If you burn a book on Earth, it turns to ash. If you drop that same book into a black hole, it fades to nothing. Both look like destruction, but in physics, only one of these events is considered a total impossibility. To understand why, we have to look at quantum information, the physical arrangement of particles. Take a group of carbon atoms. Arrange them one way, and you have coal. Arrange them another, and you have a diamond. The atoms are identical. The information is in the pattern. Quantum mechanics states that this pattern is indestructible. You can shatter a diamond or vaporize it, but the universe keeps a perfect trace of where every single atom went and how it was spinning. Theoretically, if you could track every wisp of smoke and every unit of heat radiating from a fire, you could reverse the math and perfectly rebuild the original object from its remains. The universe has a flawless memory. Because every physical interaction is reversible, the history of the cosmos is never truly lost. It is simply scrambled. Black holes represent the only known threat to this universal law of preservation. In 1974, Stephen Hawking used quantum equations to show that black holes are not static voids. They actually leak mass back into space over trillions of years until they evaporate. This process, called Hawking radiation, shows the black hole shrinking as it releases energy. But there is a catch. The math suggests this radiation is completely random thermal noise. Whether you throw in a diamond or a lead weight, the radiation that eventually leaks out is identical. It carries no data about what the black hole consumed. When the black hole finally disappears, the matter is gone, and the radiation left behind contains no record of the objects that formed it. This creates a paradox that breaks the logic of physics. As information can be deleted, the present no longer contains the data needed to understand the past or to predict the future. Solving this required a choice between two pillars of science. You could follow general relativity and accept that the information is lost, or follow quantum mechanics and find a way to save it. One of the first proposed solutions was remnant theory. The idea was that black holes don't evaporate completely. Instead, they leave behind a microscopic speck, a remnant, that houses all the information collected over the black hole's lifetime. Mathematically, this failed. A subatomic speck cannot store the near-infinite amount of data from consumed stars without exceeding the physical limits of energy density. Later, physicists proposed the firewall. To ensure the outgoing radiation remembers the information it needs to stay consistent with quantum laws, a massive wall of high-energy particles would have to form at the black hole's edge. This saved the information but broke the equivalence principle of relativity. According to Einstein, an observer falling into a black hole should feel nothing but empty space. Hitting a wall of fire would contradict the very nature of gravity. By 2012, physics was at a standstill. To keep the universe's memory intact, scientists had to find a way for information to stay at the surface without burning anyone who crossed it. The breakthrough came from a concept called black hole complementarity. It focuses on a thin layer just outside the event horizon, known as the stretched horizon. For an outside observer, time slows down near a black hole so much that anything falling in appears to stop right at the edge. In this framework, the three-dimensional information of an object is perfectly flattened and encoded onto the two-dimensional surface of the horizon. Every atom is mapped as a pixel of data. As the black hole evaporates, the outgoing radiation passes through this surface and picks up the patterns of the encoded pixels, carrying that information back into the universe. This solves the paradox by showing the information was never lost, it was translated. It suggests that a 3D volume of space can be fully described by a 2D boundary. This discovery revealed a broader rule. The maximum amount of information any region of space can hold is determined by its surface area, not its volume. Because this area scaling law applies to everything from black holes to galaxies, physicists realized it must also apply to the cosmic horizon, the boundary of the entire observable universe. This leads to the holographic principle. It proposes that the three-dimensional world we see is actually a projection of data that originates from a flat, two-dimensional boundary at the edge of space. The attempt to save a book from a black hole resulted in a new understanding of our own dimensions. It suggests that our physical reality is the 3D result of a 2D interaction happening at the very limits of the cosmos.